Slide this over. All right, so we're gonna get started here on our third video. This is actually the second session, but the third video doing kind of a deep dive into Mastercam 5-axis programming. And so we really kind of started at the very, beginning with creating some surfaces, creating some wireframe, and then showing different ways of controlling curve 5-axis. So just doing, kind of a quick review here before we get started in the new content. And, there's lots of different options in every toolpath that's in Mastercam. They've kind of been changing over the years. So my intent in kind of covering and starting with curve 5-axis is to kind of start with the simplest of the 5-axis options, not kind of throw everybody into the deep end of the pool, and really, try to cover as much of the interface and as many of the controls that I personally use or have used in the past. There are certainly switches and options in Mastercam that I've never touched, but they're kind of few and far between at this point. So part of the advantage of, teaching many Mastercam classes over the years is a broad exposure to the product and the ability for me over time to ask questions. And it's through that asking questions and gaining an understanding of what people are trying to do that I've, had a great chance to dive into the different controls in these toolpaths and kind of discover, how they work. So I would just encourage you to do that. There's so many different tools in Mastercam. Mastercam is really like the Swiss Army knife of cam. So, you may end up cutting down or cutting off that branch with that little tiny saw that's on there, but it's got a tool in there to do it. So if one tool is not working, it's nice to be able to explore other options. So for example, we've picked tools, but not really talked too much about them. The tool page is kind of a standard part of the interface. The holder has been enhanced and added. So in older versions, you just picked a tool for 5-axis that didn't really include the holder definition. Now it does. And part of the reason I bring that up, if we look at things like collision control and collision avoidance, the Mastercam Curve 5-axis toolpath really only considers the tool. So to review what we've talked about so far, we've talked about cut pattern. We talked about, using chains, 3D curves, how this is very similar to contour as a toolpath. So 2D contour and multi-axis curve are very similar. A lot of the same layouts, but there are some important differences. So the ability to modify the radial offset, shift the tool to the right or to the left as an offset from the center line of the geometry, no matter what is selected up here. So even if I'm in computer, I can set this to 0 and I get center line of the tool, even though the picture shows left. So if I am going radial offset 0, I will often just turn this off so at least the picture looks correct. Curve following method. So we have an accuracy tolerance, a cut tolerance, which is a linear tolerance from the geometry that you are driving. And along with this linear tolerance for accuracy, we have this maximum step parameter. And so this is where we were successfully able to take this toolpath, and you can see I've got, let me go ahead and go to levels. I'll turn off the vector lines. You can kind of see them very well against this background. But you can see that each one of these vector positions represents a tool location in space. And so if we look and we open up this little back plot and hit S, you're going to see these coordinates, and those tip coordinates are what are going to come out in your NC code. So the start position of this toolpath is x.75, y positive 2.8856, z 4.0. If I take and post that path, what we should see is the connection between the coordinates that are in the NCI data and the actual values that are coming out in our code. So that start position is given by the first vector in the path, and as we backplot through here, we're just going point-to-point moves. These point-to-point moves are output in the NCI as NCI G code 11, and that NCI G code 11 gets converted into G1, and the post processor looks at these vector angles and these vector positions, which is both a position and an orientation in 3D space. So as I rotate it around, you can see these are vectors. That represents rotation. So whenever you see a vector, if I look at this from the, say, back view, whenever you see a vector, and I'll back up here a little bit, that is changing between tool positions, let me go into my options here. There we go. And I'm gonna turn up the translucency of the tool so we can see it a little bit better. And I'm just pressing S on the keyboard. And when I press S, you'll notice these coordinates changing. And so every vector represents potential rotation, and that rotation occurs from the post processor. I'll just rotate the perspective slightly. So we're rotating through there. And then even as we step across here, we go back, what you'll see is that we're changing angles. So there's a progression where this angle changes from, I forget what it is, 67 to 70 degrees, something like that. So that's why we're getting these additional vector positions that are output as we transition through the corner, because our vector lines have different tilts to them. Okay. So we talked about the connection between the NCI data, the vector positions, and using this maximum step to reduce the total number of vector lines. One of the nice things that they added in, I don't know, Mastercam 2021, it's pretty recent. It certainly wasn't in X9. If I change, for example, this maximum step, let me change it back to 0.1. I can hit apply and I can regenerate the toolpath from within the dialog. So I no longer have to close out of the Mastercam toolpath to see those changes update. And you can see this is fine. This path would cut beautifully on the machine, but what's the problem? From a code perspective, it's not going to affect how the part runs at all. But from a user's perspective, this is what they see in the code. Okay, so this is dropping, right? We're getting all these Z drops. That's fine. This is fine because every line has a change on it, right? One of these numbers is changing, maybe both, so that's good. Then we get down here and we see this. What is this? Well, basically between here and here, that's a waste of memory. We're literally moving to this XY position, Y is not, X is not changing, whatever, We don't need to output these redundant positional moves where we're just moving 100 thou per step if we're operating in a straight line without rotation. So again, we played around with this. I think we tried a value of 10 and it was really wonky, didn't give us great results. Let's try 5. I mean, that works, but this is weird. Let's try going back to 3. There we go. So there's something magic about that 3-inch number with this particular path that's giving us these good results. What's a good result? What's a good result for a 5-axis toolpath like this? Why do I think this is a good result, whereas what we had previously was a bad result? This is a clean toolpath to me. This is the standard by which I judge every other programmer in the world. When we're creating a path within reason, does it have kind of one high start point, which is the safety block that you're going to see in your NC code, a nice, safe, clean, smooth approach? Now, I'm not saying that the parameters that we input are perfect at all. I'm not saying this is a great toolpath in as far as how it cuts. What I'm saying is visually, what is the overall visual presentation of the toolpath? Are there a bunch of extra retracts? I call it the sewing machine motion, where somebody's cutting along, bzz, they make a little cut, they jump up, they jump back down. Bzz, they make a little cut, they jump up, they jump back down. Now, if you're cutting one way and the material requires it, there's a million different reasons why you may want to retract for your reposition. What I'm more gauging is, does a guy have a bunch of extra retracts that are really high and wasting a bunch of time? The other thing I'm looking at is the code, does it have some type of filtering associated with it? Whether it's a thing like a maximum step on a curve 5-axis, which is an input, or like an actual filter that is cutting away geometry. What I want to see in general from a 5-axis path, now, could we use smaller values for the approach? Of course. We don't have to do such a big approach. We can modify a whole bunch of stuff, right? But what I like is one clean, high approach point, some type of entry that's nice and smooth. I'm cutting around, and in areas where I'm just doing linear interpolation, I don't have a lot of extra moves, because any extra moves in here is going to be moves in my G code. And the final piece of the puzzle for a 5-axis, I want smooth rotation on the machine. And that generally is going to mean more vectors for rotation, a combination of that, and even spacing between the vector positions within reason. So here, this is going for, 100 or 150 thou between, and then it jumps down to like maybe 80 or 50 thou between. I don't care about that. That's going to be fine, because if I look at this from the side, I'm getting rotation. Now, did I make my maximum step of 3 inches too big? You notice what do I see here? As I rotate this around, this looks to me like the tool's going down along one angle vector and then changing direction. So I'm getting, if I can show it in the best light, I'm getting what I would consider almost a kink in the toolpath right here. A little weird step directional change. And that could be from too high a maximum step. So let's try 1 inch for the maximum step. That'll be a good combination of filtering. Oh, look at that. That cleaned up at least over here. And I may have something going on with the particular vector in there. You may have a little wiggle to it. I just kind of sketched this stuff all out really quickly. But I'm looking at the amount of vectors to judge what is the quality of the toolpath. And that looks pretty good, at least especially along here. Now, I would probably stick, to be honest, guys, if I've got a problem interpolating between these two vectors because of my step or whatever, I might try to create some interpolated vectors along here. I've got one vector at one angle. I've got another vector at another angle. If I look at this from the front, you can see the distance between the two. How would I construct an intermediate vector between these two lines?
Match them.
Well, I know I'm going to use the midpoint here. So, hey, I've got a line here, I've got a line here. I kind of want to do a smooth interpolation between them, but I want to follow with the tip of the tool this line. I mean, that requirement hasn't changed. So, but I know if I want to create one in the midpoint here, or in the middle, I can use the actual physical midpoint of the line. So I'm going to go into wireframe, create line endpoints. I'm going to right click, and I'm going to be sure that I am in the 3D mode, not 2D, because otherwise it would only let me create at a certain depth if I'm in 2D. So I'm going to highlight the midpoint of that line. Now it's stretching out another line kind of anywhere in 3D space. How can I find the midpoint between these two lines right here? Well, in the old days, I would actually create a line physically that joins them, and I would use the midpoint of that new line. I would create a piece of construction geometry. I can actually, though, do a temporary midpoint. So I'm going to put my cursor on the endpoint of that line until I get this little green dot, and then I'm going to do the same thing on this other one until I get the green dot. And when I do that, it gives me a little red dot that I can use as my middle position. So I can continue doing this, right? I can, break this line or create a different line, and I can just connect endpoint to endpoint and then midpoint if I need to generate additional vector lines. And there's, other techniques that we could do if we needed to create lines or other geometry to control the path. But this brings us into the other thing we talked about, which is tool axis control. The curved 5-axis toolpath has a very simplified interface. I like to think of it with the idea of it's very similar to a contour-based toolpath. We're describing essentially a chain of geometry that we want the center line tip of the tool to follow. And as it traces that geometry, we may or may not have an offset to the left or right. And we may not necessarily be compensating to the chain itself. We may be compensating, for example, to a surface. Okay, so under the tool axis control piece here, we have tool axis control lines. That's what it's currently set to. I'm going to select another line. And if we generate that path, still got a little weirdness here. Not 100% sure why, and it could be because tip of the tool contact point is changing as we kind of traverse this geometry. We'll talk about that. So line distance from curve, you can set a limit to say, hey, if I've got a bunch of lines selected and that line isn't within a certain distance of my geometry, don't include it. Honestly, never used that particular control, line distance from curve, because generally speaking, I'm going to go through and click the vectors that I need specifically and remove the vectors that I don't. Other thing we talked, I don't even know if we talked about it. Collision control. So we've really focused pretty heavily on, cut pattern and tool axis control so far. We talked just very briefly about linking. We talked very briefly about roughing. We added some multi-passes as an example and looked at the step over between them. And then in linking, we talked about entry and exit, how to use it, how to generate additional vectors by modifying the curve tolerance, how you can use closed loop overlap. So for example, if you're in the interior of a pocket, especially one with closed walls, how you can generate, a safe entry motion to get in underneath the cut, make your cut, and then retract safely with a lead out move, and then finally exit. So I enabled collision control previously, but I didn't really talk about it. So let's look at some of the options. I'm going to turn on collision control, but I'm going to say, hey, don't worry about if the tool is gouging or not hitting. Just compensate to my selected curve. So I'm going to disable this surface because we're not on comp to surface. And I'd say OK. And if I backplot, well, and we are center line, we are off. Oh, no, we're not. Let's go off so that we can see the comp to the curve. So one more quick change here. We're going to go off, and we're going to set our radial offset to 0 so that we're going center line of the geometry. I'll turn off my vector lines, and we'll backplot. Okay, so let me just get rid of this. Let's move this to level 6 where we have our other vector lines, force it to be off. I'll also save the file, and I haven't played too much, but I've been playing a bit. So I'm going to go into File and run Repair File. This is the old RAM saver. I'm going to say no to delete duplicates and no to the parallel arcs. It tells me it's decreased by a little bit. And so I'm doing a save as to give me a nice clean version of the file. All right, so if I backplot this, it's fine when we're essentially running in 3-axis. But what happens when we tilt the tool? You guys see what's happening here? We're driving an axis line that goes down through the center of the tool. We're driving a vector. And that vector, the tip of that vector represents the center line of the tool, and we're forcing the center line of the tool on to be on the geometry. So the tool vector is different from what we would consider the contact point. The contact point is the point on your tool that is actually tangent to the surface that you're driving it. Guys, this is the reason why, if you've ever had problems in Mastercam with driving a 3D contour, this is why the 3D contour does not do accurate compensation. And that's why they came up with the toolpath project. So a 3D project style toolpath takes some kind of 2D pattern, whether it's geometry or whether it's a toolpath, and it projects it down onto a set of surfaces so that we can fix this problem, the problem of tool gouging. And so this is what we get when we just say, hey, I just want the tool to compensate to the selected curve. I think there is the most extreme tilt. Let's make it real extreme. Let's make it real obvious. So I'll go to the levels. Let's turn on the vector lines. Let's get rid of that one. Let's go to our planes, and let's just go front. And I'm going to analyze that angle. And it tells me relative to the front plane what that angle is. Make it 52. I'm not going to change anything else, just the angle. Change my toolpath back. Let's regen that. Go back into backplot.
So you just change the angle by analyzing it?
Yes.
How long has that been a thing?
It's been a thing for a long time in Mastercam, but there is some caveats to it. So, for example, if I go back to levels and I look at my vector line and I analyze this angle right now,
Right.
it tells me it's 0 because my plane is set to top. So 0 degrees in the top plane is pointing facing to the right. So doing this with any one angular plane is pretty easy. If you have a compound angle, it's a royal pain. Like it doesn't really translate if you've got a line that's tilted in multiple dimensions. In that case, I would recommend like the transform. But if you're just trying to get a line and adjust the angle, this works pretty sweet. And so to make it work, we're going to go to planes and I'm going to set my tool and construction plane to front. So now with the front plane selected, that is the flat view. 0 degree angles are going to be measured from positive X and they're going to go counterclockwise. So positive X is 0, positive Y is 90, negative X is 180, and minus Y is 270. So that's how I'm looking at this. Now, in order, so I can just, set the angle here or analyze the angle, but it's also relative to the end points. So right now you can see my start point is down here. My end point of my line is up here. So the angle makes sense. If I reverse the endpoints, this button, by the way, is new. The reverse endpoints and these little endpoint auto cursor buttons have been around for a little while. I don't know. I can't remember if they might have been in X9. Like guys, honestly, I've been using Mastercam so long, my memory of the old is kind of fading a little bit, as it should be, right? As new stuff comes to light. But these little attachment buttons are super useful. So whichever one is the start or the end point, like I know this is green, so this is the start point. This one is red, so the triplet of numbers, the XYZ over here is the red. If they're backwards, so if I hit this reverse, look what happens to my angle. So it gives me the complement of the angle. So again, I have to make sure, that the start point of my line is in the correct end of the vector, end of the line that I'm editing. But then, yeah, as long as my plane is correct, oh man, it's sweet. And it also gives me the 3D length at that angle. So if I'm like, 3 inches is not what I want for that line. I really wanted that thing to be, 1.75. I can make the edit here. And as long as I've got my start point in the correct position, it shrinks the line the way I want it. If I go back to 3 inches and I have my endpoints reversed and I'm saying, oh, I just want it to be 1.75 long. Now all of a sudden I'm going the opposite direction because it's always going from the start point to the end point for both the angle and the length. So now I might go, I just reverse these. Okay. So yeah, so that's been a kind of a cool function that's been there for a while. The other thing I recommend you guys always do, guys, make sure your precision is precise enough. 4 decimal places is never precise enough because there's always rounding involved, even when you're just creating, regular geometry from the outset, but especially when you're dealing with customer geometry. I would say the minimum here is millions, 6 decimal places. You get a pretty good idea of what's going on, right? Because you can say, okay, in my code, I'm getting 5.2221, but there's still 28 millionths. It's less than 50 millionths, so it's going to round down. So that's why I'm getting that number. But there's still these remainders that are left over, and this precision critical when dealing with arcs. When is an arc not at 0, 0 in X and Y? When it's really at 0.000021 in X when it's at 0.000034 in Y, right? You can have these remainders of millionths of an inch that will affect things like arc breaking, tangency, whether or not endpoints line up. So just something to be aware of there. I would highly encourage you to increase the measurement precision. Let's go back here. Okay, so we got some lines. We're modifying those lines and we're compensating only to the curve. So we get these vectors, but then as the vectors rotate, ta-da, we get gouging. And so what we have in the curved 5-axis toolpath to compensate for that is what's called collision control. And if I could go back 30 years and talk to the guys at CNC Software that were designing these paths in this interface, I would, let's say it in a polite way, I would make a request that they take the word collision out of here. Because what do you think of when you think of a collision on a machine?
Bang.
Crash. Okay, so collision control, I wish it was really called, tool tangency control, maybe something like that. Tool tip, projection control, something like that. But let's talk about a few things before we do comp to surfaces. In contour, you have a depth parameter that you set. You'll notice under cut pattern, you don't. This is all about the XY visually, right? I mean, it's not XY, it's not really the same thing. But this is all about following the contour. In collision control, we have a vector depth. So if I set this to 0.5, I've just offset the tooltip from the chain by ½ inch. If I set this to, minus 0.21, this is my depth control. Vector depth is the depth plus or minus whether or not I'm offset from the depth of the chain. So this is where I can set a positive offset up or down in Z, conceptually, right, from the depth of that chain. But this is because I'm using on selected curve. Now, if I go to comp surfaces and I add a compensation surface, so I'm going to add this flat floor as my comp surface, I get both vector depth and stock to leave. Really, because I've got a flat plane here, they will function kind of exactly the same. So all I did was I added a comp surface. I told it 0 stock to leave, 0 vector depth, everything the same. And what we're going to see, all this should look the same directly from the front view. As I rotate the tool, look what's happening to the height of the vectors. As the tool rotates, the height of the vector increases because the angle of the tool changes. What we're doing is we're maintaining the tangency of the tool even with that vector as the center line of the tool. Now, what does this require? Well, look where my line is that I'm driving, right? Look where my contour is. Look at how far out that contact point is that's outside of that geometry. Does everybody see that? So what that requires is a surface, like I said before, that's more like a runout surface. You want the surface that's part of the compensation of the toolpath to go and extend, at least, in my opinion, by the radius of the tool beyond what you're driving, so that it can always maintain the proper tangency and you don't see the tool all of a sudden drop because it reached a place where there's no surface here and it's like, oh, I can get closer, there's nothing to hit, and so it'll drop, right? So by the time we tilt all the way over, but how much it's raised that tip. So what do we go with? End up with 50 degrees, something like that. And now we went from 50 degrees to straight up and down. Let's show this again. Within this span, from here to here. So I would expect an even more extreme drop as we transition that tool. So you'll see it here. Now, one of the things I can do to help me visualize, I've got geometry. I'm going to select that geometry. I'm going to get out of the toolpath. Show it in this dark green color. And I just picked this dark green because it's different from the blue. Different enough that I can see it. But what do I got here? I have a transition from one straight line to another. I have an endpoint. So I'm going to go to the home ribbon and I'm going to turn on endpoints. And unfortunately, I got a 4K monitor, guys. So like, I don't know if you can see like the one pixel that's white on there in the display. It's actually really hard to see because of the 4K monitor. I mean, it probably also doesn't help that I got old eyes at this point, you know, birthday's coming up. So, but
Happy birthday.
What's that?
Happy birthday.
Oh, thank you. Thank you. That's this month. So,
You can see the spec.
What's that?
I can see the spec.
Okay. It also helps if I make the line width narrower. So I selected all the geometry. By the way, what I did was I just held down Shift on the keyboard and then clicked. And because there were no other endpoints, that puts me in wireframe chaining selection mode, and it selected the whole chain. And then I just right-clicked to get access to that little kind of mini attributes bar. And I clicked the drop down for line width, and I selected, you can see, as I highlight the different thicknesses, it'll change them. Let's go with next to smallest. We'll do that one. I'll save it. Okay. So we have the ability with this curve 5-axis to maintain that tangency control with this collision control. And I can still do vector depth or stock to leave. Really, they're one and the same at this point. Why they have both, I honestly tell you. Maybe there's some important reason. I'm just not aware of it. So let's say, hey, we're going to leave a millimeter. We're going to leave 40 thousandths of an inch. Now, all we did was we took the whole toolpath and we said, hey, everywhere that you're driving, I want a little bit of stock to leave. And, you know, whether it's vector depth or stock to leave, the tangent point of our ball should be staying exactly the same height above, even though the center line of the vectors is raising, the tangency point or the plane of tangency is even. Kink was fixed somehow. Yeah. That's a great point. So sometimes you can make a change in one little area of the toolpath and you feel like it's totally unrelated, but remember how we saw that kink in here? Now it could have been because I had something else selected for the comp surface, and then deleting it and reselecting it helped it. It could have been the offset. I mean, we can always go backwards. Oh, by the way, if I've made a bunch of changes to this toolpath and generated between them, I'll actually get the option to kind of roll back those changes by changing the interface settings because it remembers kind of between your saves. It's like Jeff's typing a question here. Yeah, and that's a good point, Jeff. It could have been the line angle, something about it's just so hard to say sometimes which particular change as I was going through this in the process resulted in this part of the toolpath being fixed. We did add that extra line, but even after adding that extra line, I still thought I saw a portion of the vectors near the transition corner that looked funky, like there was that weird kink in the toolpath. So all fun stuff to explore with learning 5-axis for Mastercam curve 5-axis toolpath. So if you ever run into any composite situations, you're cutting some kind of honeycomb core with skins, you may need to take advantage of this oscillate function. So what does this do? As you're running around your contour, it raises and lowers the depth of the tool, either in a linear fashion or in a high speed, which does these little high speed loops. So we can do something like distance along the contour. Let's say, every inch we're going to vary by a 1/4 inch. And if you're cutting aerospace composites at Boeing, I can tell you we use this a whole lot because it spreads the wear of the tool, because those skins are very abrasive. So it spreads that wear over the flute length, and helps your tools last in many cases, sometimes up to 10 times longer, because you're not wearing just a wear line just where you're contacting that skin. Now, most of you guys are never going to use that control, right? Unless you're doing a real specific application, it's like, yeah, I don't want to do that. So, I just wanted to point it out, kind of talk about it for a second, tell you, what it's for. The other situation that we'll run into is where we need a check surface. And in general, a compensation surface in Mastercam is something you want to cut. A check surface is something you want to avoid. But in 5-axis, it's often sometimes better to just add an additional compensation surface and offset it, because if you just put in some kind of avoidance surface, now Mastercam has to decide what to do. How is it going to change the toolpath to give you what you want? So let me just do this and make sure I'm in the top plane, which I'm not. Top plane, I'm going to be 2D, Z depth, let's go 0.875 inches. And I'm going to go in here and do wireframe, rectangle, and I'm going to create a surface with that. Let's go right here. Okay, great. I've got some surface. Let me change the color of it. Some surface that I want to avoid that's along my path. Generally speaking, when we run into a check surface, that's going to cause a retract. And because we've got it set probably to always use, remember how we were using multiple passes. So what that did, because we had always use turned on, it's like, oh, I want to avoid that, but hey, I also want to do a lead in and lead out from it. Well, do we want that lead in and lead out there? Maybe, maybe not. If we turn off always use, what do we get? Now we get, okay, I hit this surface, but do you see where the tip of my tool went? Because we didn't use any stock to leave, and because our retract height is so low, it's like, hey, as soon as we get to this vector, I'm going to create my next vector. My next vector is in contact with the check surface. Therefore, I'm going to remove that vector. And anywhere there's a vector which would intersect that surface, I'm going to remove it. And I'm just going to connect those with a rapid move at our retract plane. That's why you can see this is a longer distance here and this is a shorter distance, because there were vectors in between here and they just got moved. So if I really wanted to do this and there really was something that was here that I wanted to avoid and it was, that exact shape, well, I'd probably want, a much smaller step. So I go back into my cut pattern here. And in that case, I'm going to keep the 1 thou. I'm going to change my maximum step to 0.1, but I may also want to force a whole bunch of vectors because I could be within 100 thou plus or minus of the edge of the surface because this is just a maximum step value. So I'm going to leave the maximum step at 1 inch. But then I'm going to come up here to my distance increment. This is forcing an absolute spacing between the vectors. Let's go 4 thou. Now, when I do this, as you can imagine, I'm going to get, a wall of vectors. But now I can guarantee that I'm within plus or minus 4 thou of that edge, really within 4 thou of that edge. And this is where, even with distance increment turned on, I can probably do this filter. And so that I don't get too much of the rotation, I'm going to go like 25. I want to look ahead 25 vector positions, and I want to do this one way. I only want to go down the chain for the evaluation in one direction. This really shouldn't matter unless we're doing some kind of zigzag or multi-pass where we're doing keep tool down, but I'll just turn it on anyway. Now, will this produce a great result at the machine? I hope so, as long as the machine can smoothly interpolate between some of these other rotational positions. This should be just fine. And what this gives us by adding that filter, get our nice smooth entry. And now the filter just says, hey, we're just going from line to line. It's within 1 thou. I'm going to chop out that extra one. And here, I look from the front view, should be within about 4 thou, right? I could do a vector line every, 2/10 if I really had to get my tool exactly there. Now, if this height was really here, what else might I want to do? Let's go to our linking and use the clearance only at the start and end of the operation. And I'm going to click on the retract button and choose a position in Z off the geometry. Great. Tells me that's 0.875. So you know what? Let's add a 1/4 inch to that. I'm going to make my retract 1.125 and say OK. And now, admittedly, I'm just playing with this toolpath. This isn't anything that I would specifically cut. I'm just using it as an example to say, how do we control the motion of the tool with the tools that we've got available to us in Mastercam. And believe it or not, even with this kind of much fewer vector lines, this would actually probably rotate really well. And part of the reason I say that is because even with the settings we're using, there's a fairly consistent amount of step and angle change. A little bit more here, probably not enough to be concerning. And kind of the same thing over here, right? What I'm looking at is the smoothness and the step size between those vectors, the amount of change on the tip. That's all well within acceptable limits and results. So this would actually, if we had to do a path like this, cut really nice. Now, do we actually want some lead in and lead out? Maybe we do. And so maybe we would play with the lead in and lead out parameters. We could also play with the lead in and lead out with the always use function. But just giving you some examples of some of the stuff that we can kind of do on here. I'm going to pause and see if there's questions about the stuff that we've talked about either in last or this current class. I guess no data, no questions at the moment is good. Let's make sure what we got here. Is minimizing your vector distance a good way to reduce jerky motion? Generally, yes. Often, here's a great tip for everybody. Everybody pay attention to this real quick, because this is one of the things that comes up time and time again with Mastercam customers who are doing 5-axis. Depending on the post that they've got, depending on the particular post processor, into C, users, public documents, pick your Mastercam version. I'm going to look in 2020 first, just because I know if I mess with a post in 2020, not much is going to get broken. Okay, didn't have anything in 2020. Let's look in 2023. No posts. Yes. Necessarily the one I wanted. Okay, I'm going to pick a post processor that is for a UMC 750 that was built using a derivative of the generic Fanuc 5-axis mill post. So the generic Fanuc 5x mill post has been around for a long, long time. And it is a post where the vast majority of the controls that configure the post are set as variables. So starting at the top here, these variables kind of through here are what configure the 5-axis post. This is what tells Mastercam how the 5-axis configuration for the machine is set up. It does a bunch of other things. There is a switch that is often turned on that is only really useful for gantry machines and head table machines. Do a search for BRK. There it is. For a lot of 5-axis posts, and this isn't when the jitter is caused vectors in the toolpath itself not being quite correct. One of the things that'll happen is, say you're rotating from 0 to 90 degrees in your tilt axis or in your rotary axis. Mastercam is going to break up the rotation between those if the angle is greater than the max angle. And a lot of times it'll be set like, 1, 2 or 1, 5, 5 degrees. But even still, you're going to go from 0 to 5 degrees to 10 degrees to 15 to 20. And the Haas could be automatically clamping and unclamping between each of the rotary moves. So generally speaking, on a Mastercam 5-axis post for a Haas with a dual rotary, so a trunnion, a tilt rotary, where both rotary axes are on the part, where the part is moving, I would set brake move head and brake max angle to 0. So these guys will get you right here. Now, if the quality of the vectors is not quite right, and that's why you're getting weird jittery motion, then I would look at the quality of your geometry. So, for example, if you had, a bunch of tilt lines that you were using, are all the tilt line definitions good? Is one of these rotated either in the front or the right side plane slightly? There's all kinds of reasons that you could be getting jitter in the toolpath, but I think the secret is kind of just going through here systematically and kind of using different controls and realizing that the inputs to the toolpath are geometric and numeric, right? You're going to select geometry and you're going to type in data, and sometimes changing a number by a tiny fraction, there's some weird rounding thing inside the algorithm, and that cures it. Just like we saw, Jeff, when it was like, hey, we changed a few things and all of a sudden that weird kink in the toolpath disappeared. Sometimes it takes careful analysis by the programmer to catch these little weirdness, that's being output by the toolpath, and then experimentation to figure out what's the magic combination of settings to get that weirdness or that jitteriness to go away. Good, Jeff? Jeff, if you're talking, you're muted. Oh, did that on accident. No worries, sir. Not an issue. Okay. So, a couple more things that we can talk about for curve 5-axis. Tool axis control. We did lines, we did all the different methods. Some of them weren't admittedly the greatest examples, but we tried them all. 5-axis output, you can also limit it to 4-axis output. So even if you're driving a 5-axis toolpath, if you've got a 4-axis machine, but you've got a multi-axis Mastercam license, we can drive a toolpath that is offset from the center line of the rotary with vectors, provided we only have vector rotation along one axis. So if this, if you had a rotary 4th axis A on a Haas machine and you had some feature that was offset that had a tilted wall, as long as it only tilts perpendicular to the axis of rotation, you can limit the output to 4 axes. What else do we have in the toolpath? Well, some kind of cool features. Let's say, for example, we're machining this. I'm going to go back into the tool axis control lines. I'm going to click on unselect. I'm going to take out those 2 rotated lines. Say OK. Okay, what is this giving us now? It's giving us a 3-axis toolpath. I mean, it's vector-based, but it's a 3-axis toolpath. If I post that out, it's going to be all linear motion. It's going to be all G1. For a BC0, you shouldn't see another BC in there. Okay, no rotation. Well, that might be the shape of what we want to cut, but we got a 5-axis machine. So let me do this real quick though, guys, just so we're not muddying the waters. I'm going to go into collision control. I'm going to go to check surfaces. I'm going to remove my check surface. I'm going to select that geometry. Let's move it to a new level. Let's make it level 7. I'm going to name it on the fly. Turn the visibility off. Okay, so now it's just a 3-axis path. Well, if I'm cutting this, especially in some nastalloy, right? Nasty alloy. It's a little portmanteau. I'm going to go in here to the parameters. And we're going to go to tool axis control. And let's look at lead and leg. Lead and leg is automatic tilting. Lead is to tilt forward in the direction of cut. Leg is to tilt backwards opposite the direction of cut. So if I gave this, say, a 25-degree lead angle, let me also do this because we've got our filter turned on, just so we can clearly see it. I'm going to disable the filter. I'm going to go back into the cut pattern. I'm going to turn off the distance increment, and our maximum step, let's just make it a 1/2 inch. So we're entering in, and we're already tilted forward. So now it's got to figure out how to do the transition. So this gets to be a little awkward because we're using lead and we've got a sharp corner in here. It just has to figure out how to do that transition. Now, would I run the path specifically like this? No, probably not. But I'm showing you kind of what's available. And sometimes even, say, a 10 or a 15-degree lead or whatever angle change, right? Sometimes, tool axis control, this can make all the difference to get the contact point of the tool on the tip where you've actually got some flute instead of on the very center, where even with a center cutting tool, your effective RPM approaches 0. Right? So we got a 5-axis tool path and 5-axis machine capability. Let's rotate the tool so that the contact point on the ball is much more where the areas where we actually got flute that's capable of making the cut. So 15-degree tilt. Now there's some rotation as it goes to the next section. 15 degrees. Figures that out. And again, we took out these tilty lines, so we're only tilting in the direction of the tool. Now, I tend to not use lead and leg a lot because of some of the issues with rotating at junction points like this. But side tilt, I use this bad boy quite a bit. So if we give it 15 degrees of side tilt, again, keep in mind we got to know what the direction of tilt is, or excuse me, the direction of our chaining direction plus what side we're on. But this is positive side tilt. It also, and the same is true for the lead and lag angle, will accept a negative value. So if I tilt negative 15 degrees, that that looks much more like something I'd run. It's making a smooth transition at the corner. It's kind of fanning and arcing out. Even the transition between these is pretty good. If I don't want as many vectors, remember what's causing the extra vectors for rotation? Tool axis control angle increment, quarter degree. I've used as small as, 1/100th of a degree, but somewhere between 3 degrees and a half degree is a pretty good value to use. So this would be buttery smooth and actually a pretty decent tool path if we had to cut this square. And by doing that, we also wanted to rotate. Let me go right side. We wanted to rotate this 15 degrees, so now we're cutting here. More is better when we're talking about tilt. The further we can tilt on the ball, the better results we're going to get, provided it actually works and runs with, any other geometry that we might have to avoid, etc. So if I said, minus 35 degrees, this is going to be even sweeter. But you notice as it rotates, it has to compensate as well. So that can be an issue. But run. So now it drops down. This is that nice flat surface. Oh, we're staying a millimeter up. So let me take out that vector depth just so we can see it. So collision control, vector depth, or stock to leave 0. Oh, why aren't those vectors? Why are those vector endpoints still above this flat surface? Well, because it's the tangent point. Now the tangent contact point of the tool stays tangent to that compensation surface, even as the part, remember, when we're doing this, what's happening at the machine? At the machine, that tool is vertical, right? And as it rotates, the whole thing is swinging around. So there is an option in here that will let you simulate a rotary axis, and it'll actually let the tool kind of stay vertical and the part move around it, but it does not work in 5-axis, only in 4. So at that point, you're going to want to go to machine simulation to see the actual how it would look on the geometry, right? But this is the table, just like tilting and rotating around, right? In this case, what we would typically see is the B-axis would kick over at negative 35 degrees. The tool would come down, and it's going to change in XYZ as that platter rotates around through 360 degrees or potentially a little more, right? So that's going to end. It's going to pop off there. Okay. I know I've used this projection before. Nope.
Oh yeah,
Oh,
that's
it's only with
causing a
surface.
bugger.
What's that?
That's causing me some real problems here in the last few days. I had a real problem with this where it wasn't projecting the entire contour to a surface. I had to switch the plane.
Mm-hmm. Yeah, sometimes, you can use a tool in a certain way and everything works out great, and then all of a sudden a new thing comes out and it's messed up. Okay, let's see here. Let's see what it has to say. Give me a sec here.